Hi guys, welcome back to another video of me teaching, and today I have the 2025 question 3 IMO part 1 for you guys. So why don't we just get into the question. This question looks a bit scary, right? But don't worry, let's read it together. We have a function f, which is an end-to-end function, and this function is a bonza if f of a divides b to the power of a minus f of b to the power of f of a, for which a and b are positive integers. And for all n in positive integers, find the smallest c such that f of n is less than or equal to c times n. It's a bit hard, right? Don't worry. The first thing I'm going to do is I'm going to define p, a of b, to be a property ab. And I will define this property to be just the original definition of a bonza function. So it will just be f of a divides b to the power of a minus f of b to the power of f of a. Okay? So we know that this condition must satisfy for every single positive integer a and b, right? So why don't we try and first go with a simple case. Maybe a and b are both equal to one simple constant, maybe n. So why don't we define a new property, p n of n. This will be f of n divides, using this, n to the n minus f of n to the power of f of n, right? Now we know that this must be true, right? And we know that f of n must divide f of n to the power of f of n, right? It's kind of the definition. So if this is true, then shouldn't f of n have to divide n to the power of n? Yes. Well, in my videos, we like to do a bit of guessing, right? So shouldn't we guess f of n just to be equal to n? And this type of function is actually called an identity. And to shorten it, I'll just write id. But in this case, we see that c will just be 1, but it's too easy. So this is probably not the case. So for the proving of part 1, we're just going to assume that f of n is not an ID. Okay, so I'm just going to rub this out. Okay. So this question is about number theory, right? And when there comes the divisibility branch of number theory, we like involving prime numbers. So why don't we just try and plug in a random prime into here? For example, p, such that f of p will divide p to the power of p. Okay, so if this is p to the power of p, then we must know that f of p must be some power of p, right? Because this is just p times p times p lots of times. So now the f of p must be some power of p because p is prime. So we know that f of p must be equal to p to the power of k. And we know that k goes from 0 to p. So what if k is not equal to 0? Well, if k is not equal to 0, then we know that p can divide f of p. So now that we have this, we can create a new property. We define property Pn. So we can use this original definition so that f of p will divide n to the power of p minus f of n to the power of f of p. And now we can actually use Fermat's little theorem, because Fermat's little theorem says that n to the power of p is just congruent to n mod p. right? But how do we use Fermat's little theorem for this? Well, we know that f of n to the power of f of p is just equal to f of n to the power of p to the k, because we already defined that over here. So, how do we use Fermat's little theorem? We need something to the power of p, right? Well, we can do that by, we can just change this power into p to the k minus 1 and raise everything to the power of p. So now we know that this whole thing is just congruent to the inside mod p. But then the inside is congruent to p to the power of k minus 2. And if we keep repeating, then we see that this thing, f of n to the power of f of p, will at last be congruent to f of n mod p. So, if n to the power of p is congruent to n, f of n to the power of f of p is congruent to f of n, then we know that f of p must divide n minus f of n. So we know that, I'll work this out. Since p divides this, then we know that p must divide this as well. And this is also a very important identity, okay? Because this is actually, for some values of p, impossible. Because there are infinitely many primes in the set of positive integers, right? But this n minus f of n is just a given positive integer. So there are only finite values for n. So how can an infinitely many thing divide into a finitely many thing? Well, it can't. But it only can't for large numbers of primes. So this is wrong for large primes. So we know that for large primes, we know that k must be equal to 0, because we first assumed that k is not equal to 0. So if k was equal to 0, then this p divides f of p would be wrong. So for large primes, k must be equal to 0, which means that f of p is equal to p to the power of 0 equals 1. So this is also a very, very, very important thing. So I will finish part 1 for now, and in part 2, we will do some further proving. So I hope you guys enjoy my video, and if you want more videos like this, please consider liking and subscribing. If you want to master something, teach it.